So I'm here to talk to you today about advanced technologies and just give you an overview of sort of things that you probably already know, some things about technology and how it's changing. But maybe there's some things that you haven't thought about yet, and I'll try to give you some different ideas on how you might be able to solve those problems. So let's say you're in the driver's seat. How many of you are in marketing in the audience? Anybody? So somebody's giving you a specification, right? And they're telling you, you have to build your product and it has to be better. This generation has to be better than the last generation, right? And so it doesn't matter, it doesn't matter if you're in networking or if you're in mobile or if you're in computing, whatever, your product has to be better this time. It has to be faster, it has to be lower power. You have to fit more functionality on that chip. And so when you do that, what happens to your memory content on your chip? It grows tremendously. And what does memory do to you? Potentially, memory is the big dog that may take you down, right? That's the thing that you really need to be able to manufacture. You really need to be able to understand that well. So if you look at your chip, that memory content is growing and growing, and you're having to manage that. Well, at the same time, you're dealing with your technology that's reducing from 28, which we understand pretty well, but now we're looking at 20 nanometer, 16 nanometer, 14 nanometer, and then you've got, oh, is it FinFET? Is it FDSOI? What decision is it that I'm going to make on my process, and how do I make that decision? And then with that, how am I going to actually get to the power, the performance, the area that I need for that particular chip and be able to manufacture it? So that's really what this talk is about. Just kind of looks at the challenges as you're in this driver's seat trying to make those decisions, and sometimes you actually might need some help. So if you look at the market requirements and you compare those to the technology challenges that you have, you're having increased density. You have to pack more stuff into that chip. And with that, you have a variety of memory architectures that you have to take care of. So, you can't just do your whole chip with a vanilla SRAM. You've got different functions. Some things might have to run at lower power. Some things might have to be shut off. Some things have to be parallel processed. So you might need special bit cells for that. And how can you accommodate that? At the same time, you have to meet your higher performance, and you want to have a reduced power density. So here's your market requirements on one side, and on the other side of the scale, you have all of these challenges that are being thrown at you as you move to FinFETs and FDSOI, and how are you going to be able to scale? But more importantly, how are you going to be able to handle all of that SRAM that has all of this bit cell sensitivities? What is going to happen at that point, and how are you going to mitigate that? This list over here, talking about FinFETs and FDSOI, this is just, there is no clear answer right now. There are several panels that are out there that discuss which is better, FinFET or FDSOI. What is it that is going to best match my process, right? Some of them, if you look at FinFETs, for example, they're sensitive to geometry. You have your fins. What happens with those fins and being able to manage variation, etc. And then with fully depleted SOI, here you have a process that's fairly similar from one generation to the other. But then again, there are other things that you have to take a look at. One, people tend to say is better with lower leakage. Another, people tend to say might be better for higher performance. But there's really no clear answer. If you read all of the articles, if you study this, there's not necessarily the right answer when you look at each of these aspects. So if you look at SRAM in particular, SRAM has had a very difficult problem scaling from one generation to the other. If you look at the logic, it's pretty regular how it's been scaling from one technology to the other. But if you look at an SRAM bit cell, for example, and if you look at, let's say, just a general foundry presentation that's out there, you'll go to a symposium or what have you, and they'll say, oh, you're going to have this performance and this leakage improvement from one technology to the other. But if you look at the memory in particular, that's not necessarily the case. The leakage aspects of the memory has not necessarily been scaling. The performance has not necessarily been scaling. And the problem is because there's been so much variation on chips, so much variation in the process. So people have been having to develop new design capabilities, new characterization capabilities to be able to manage that variation, understand it, and predict it in silicon. And then, of course, you have NBTI and PBTI that you have to worry about. On the cell stability side of things, I keep wanting to pointer and I'm hitting the wrong button on that. Is it this? Yeah, it's kind of small. But if you look at from a cell perspective, you have to worry about stability. And one of the things that has happened at 40 nanometer, for example, you could reduce voltage and the bit cell would be able to handle this wide range of voltage. You could go from VDD plus 20%, minus 20%. You had a really good time out there being able to really tweak your design and give yourself a wide performance range, and the memories would be able to keep up with that. But now that's not the case. Now that window is getting smaller and smaller. At 28, it was plus or minus 10%, and now you're seeing that you're having different voltage requirements for your memory versus your logic today. So now you have to manage potentially multiple voltage rails on your chip. How do you do that? And then there are the circuit design techniques that will help you with that. But what happens here is if you put all of these techniques on your chip, let's say every memory had all of these techniques incorporated, your area is going to be very large, some of which also affect power, not in a positive way, but in a negative way, some of which affect your performance. So you need to be able to select and understand from an IP provider or as an IP provider how to put the correct mix of these. Also, how to study the technology and understand whether or not they're needed, okay? And then on the architecture side, whether you're picking FDSOI or FinFETs, those bit cells are going to be fairly controlled by the foundry, right? So the days of us being able to sort of tweak bit cells and be able to sort of perform some sort of differentiation with those are kind of dwindling at this point in time. So with these emerging devices, we need to really understand for our market, for our product, which is the right decision to make. And having a company out there who's been able to really look across in a broad way all of these processes and has some background and understanding that will be beneficial to you. Maybe you make a selection and then you find out that some part of that selection in that process doesn't work for you. Maybe you need to tweak it or you need some sort of customization to meet your needs. Then you need to be able to find a partner that's going to be able to support you in that. If you look at SRAM scaling difficulties in particular, you know, SRAM itself, if you look from 90 to 65 all the way down, you can see that the SRAM, here's your logic gate, okay? Here's your length of your gate for your SRAM. And look at where it sits in comparison to the same blue line for logic. I mean, the scaling has just not been able to keep up in general. The other issue is that with all of the variation, a lot of characterization has to go into memories in particular. So a lot of Monte Carlo analysis, a lot of runtime. So actually creating memories, which seems to be very vanilla, very straightforward, the item that you should just be able to plop into your design with your standard cell libraries, a lot more work has to go in to actually make sure that they're accurate and that what you do in your design is actually going to match what you do in silicon. The other thing is that being able to keep your leakage under control. So in that case, it's not just picking your process, but it's also being able to tweak your design to be able to either manage it with power management modes, manage it with threshold VTs, etc. On the lithography side of things, what we're seeing is that when you're dealing with coloring, for example, in an SRAM, if you think about a sense amplifier, you have to have devices that specifically match, okay? Very, very, very important. And so in our case, what we're noticing as we're looking through these technologies is that pre-coloring is a necessity. But even if you pre-color, the foundries are not saying that they're going to necessarily match that pre-coloring. So all of the extraction and all of the work and everything that you're doing to try to predict this, still there might be variation that's left, okay? So solving these challenges is the main aspect as far as being able to have a product with a large content of memory that is going to be manufacturable. So when you're looking at navigating this risk, I would just like to introduce our company, eSilicon. And our company is a company that builds our own chips. So we do everything from design, manufacturing, test. We pick up the whole thing. We're a fairly large company. We have just shy of 500 employees. But what's interesting about us is that we have our own IP team. So we act a lot like IDMs, that were very vertical in the past. And our capability is that we can look at all of the IP that's out there and available when we do a chip. But then if there's some spot within that chip where we're not able to meet, maybe it's the performance, maybe it's the power budget isn't met, etc. We need to be able to go in and remove selectively maybe some functionality that isn't needed, or maybe we need to speed up a path, etc., reduce area. Any of these items, you start with something that is well understood, as explained in the previous slides, well studied, well characterized, and characterized in silicon. And then at that point, you take that design and you reduce whatever mechanism it is that you need. We have an example of a particular design where in this chip there was a particular SRAM instance that was repeated 1,000 times. And in this one instance, if we could remove a function that wasn't being used in a standard off-the-shelf compiler, we reduced the area significantly. And it was a direct, very large savings for that customer. But to do that, you have to mitigate your risk as well by starting with something that is silicon proven and by not affecting any of the paths, any of the aspects in the sense amplifier, the timing paths, etc. The other thing is within our company, we have the ability also, we have our reliability engineers, we manufacture, we study, and we understand the process. So we are working with all of the large foundries and IDMs. We have IDMs who have come to us that say, we need some special help, some expansion of our internal IP team, and we come in and we assist them to be able to give them that differentiation. They're able to do more of their IP design. And then for foundries, for example, we'll come in and we'll provide some specialty compilers, such as content addressable memories, for example. So for eSilicon, we cover all of the aspects. I keep wanting to use it as a pointer. All of the aspects of design, manufacturability, and we can tweak a design specific to your needs. This is our roadmap. And in our roadmap, we build a considerable amount of TCAMs across multiple foundries. We also do IP for IP providers themselves. So we have stepped in and we've expanded IP teams and done work for leading IP providers. On the major IDM side of things, this is really where our roadmap is in the future. We are working with several IDMs at the 20 nanometer node, at the 16 and at the 14 nanometer node. So we have a pretty good visibility, a lot of action going on in memory development and in IOs, in understanding these processes and in being able to come up with the right mix of IP. On other aspects that we have done, complete platforms for other IDMs, including ROMs and IOs. We do some DDR work as well. And typically where we come in is, we come in when there's not something off the shelf that you would just be able to pick up and use. Let's say you need some aspect of a particular IP where you might want to harden it, you might want to control its footprint, you might want specialty IOs, etc. And then on the tool provider side, we've done a lot of process development work where we have a tool that enables providers and IDMs, for example, who are developing their own processes to quickly build test chips and be able to support their PDK development. So if you look at that, you've got an understanding from the very deep process level all the way through to the ASIC design and manufacturing with our company. Other work we've done also are flash macros. So we're pretty wide and not just in process technology and understanding, but also in the IP that we develop. So in summary, eSilicon is a full provider, very broad provider of IP and chips. We manufacture chips, we design chips, we build IP that's very specialized for specific chips and markets that will enable you to get the perfect chip. That's the idea. You know, everybody has the same off-the-shelf IP, the same libraries, the same foundries, but it's selecting that combination and understanding what best combination is to use, as well as being able to differentiate in places where having a little bit of customization may give you a great benefit. Any questions?
You say like you did the fabrication also for the, so you do the in large scale, or how the capacity wise?
Oh yeah, fairly large scale. So we have very large devices that we have produced, over 300 designs, for example, manufacturing at all the leading foundries. So we're not tied to one specific foundry, and we have fairly high volume chips that we produce.
Okay.
Yes.
Thank you. Another question? Did you talk? You already spoke about your FinFET
Yes.
and the benefits to your customers.
Well, basically, I spoke about the fact that both FinFET and FDSOI are leading technologies. They both have their pluses and their minuses.
Okay.
And there's a lot of, we can share offline, you know, some of the nuances between each of those technologies.
I was walking around, so I may have missed this. What are the foundries that you were working with? Did you already talk about that?
Oh, no, I kind of stayed a little nebulous there.
Okay.
But we have some leading IDMs that we can't really mention in this talk, but also clearly Global Foundries, TSMC,
Right.
all of the leading foundries, yes.
Fantastic. Any other questions from the audience? No? Okay.
Thank you.
No.